Hello, very good day. My name is Carlos Lopez. I am Associate Professor of Sanitary Engineering at IHE Delft Institute for Water Education. And now I'm going to introduce a mixed culture steady-state model that is used for the design of the enhanced biological phosphorus removal processes. In this lecture, I'm going to talk about the principles of the model, the mass equations that compose of this model. It is important to pay important attention to the division of the biodegradable CUD because that will define pretty much the masses of the microorganisms present in the system, and they are going to be used to estimate the concentrations of phosphorus that can be removed from the wastewater. Afterwards, we are going to calculate or see the equations that are used to calculate the process volume, the waste of activated sludge to control the system, the oxygen requirements, as well as the nitrogen requirements. And finally, we're going to have a look at the CUD balance. That is a very important tool to evaluate and assess how precise have the calculations been. So first, the principles of the model. The mixed culture steady-state model has a fundamental principle, and that is that the biomass is composed of three active groups of organisms: the ordinary heterotrophic organisms, OHOs, the phosphorus accumulating organisms, the PAOs, that are the ones that are directly involved in the enhanced phosphorus removal process, and depending on how the plant is designed and operated, it may also have the masses of nitrifiers that oxidize ammonium to nitrate in the aerobic reactor. So the principles of the model are based on the estimation of the masses. And these masses, in particular the masses of OHOs and PAOs, are used to calculate the amounts of phosphorus that these two different groups of organisms can accumulate. And for that, it's important to estimate what is the split or the division of the biodegradable CUD that is consumed by each of these two microbial population groups. With that one, therefore, we can estimate the peer removal capacity of the system based on how much is stored per each population group, also considering the phosphorus that can be or may be present in the endogenous residues and in the unbiodegradable particulate organics that accumulate in the system and are coming from the influent that is treated in the wastewater treatment plant. What are the mass equations? Well, the mass equations that compose this model are all interlinked, and they are the ones that compose of the total mass of solids that will accumulate in our enhanced biological phosphorus removal system. They are composed of the volatile suspended solids or the masses of volatile suspended solids. These are mostly composed of the masses of the ordinary heterotrophic organisms and, of course, the masses of the phosphorus accumulating organisms, the endogenous residues of these two groups of or population groups, and these endogenous residues are produced by the decay or the loss of biomass that happens in the system, and the mass that is related to the accumulation of the unbiodegradable particulate organics. In addition to the masses of volatile suspended solids, we also have the masses of fixed suspended solids that will also be present in the activated sludge system. To estimate the different group of masses, therefore, we have also defined different expressions. To calculate the mass of ordinary heterotrophic organisms, it's important that we know first the flux of biodegradable CUD that is consumed by this group of organisms, the yield that they have, the SRT of the system, and this term is also affected by the endogenous respiration rate of these organisms at the temperature at which the plant is typically being operated, or in this case, the temperature of design. And this term is also affected by the solid retention time. In a similar manner, we can also estimate the mass of PAOs, but in this case, it's important to calculate what is going to be the amount of biodegradable COD that these organisms are going to store in order to, using the SRT, the yield of these organisms and their endogenous respiration rate, estimate the masses that will accumulate during the operation of the system. Of course, like for example, with the organic matter removal process, there are also endogenous residues generated by each group of organisms. First, the endogenous residue of the OHOs that is directly or proportional to the fraction of endogenous residue that these organisms accumulate, their endogenous respiration rate, the SRT, and their masses, and in a similar manner also the mass of endogenous residue that the phosphorus accumulating organisms generate during their accumulation in the enhanced biological phosphorus removal process. Then last but not least, we have also the mass of particulate on biodegradable organics that are present in the inflow of the wastewater treatment system and that will also accumulate proportional to the solids retention time. These five components make up the mass of volatile suspended solids, and in addition to the mass of volatile suspended solids, in order to calculate the total mass of suspended solids, we need to estimate what is the mass of fixed suspended solids. With regards to the fixed suspended solids, we have to estimate how much of the fixed suspended solids present in the influent will accumulate as a function of the SRT, plus the amount of fixed suspended solids that the OHOs have in their masses. These fixed suspended solids are certain minerals, certain metals that the microorganisms need and they will accumulate due to their microbial metabolism. But even more important in this particular case for the EBPR process is that we need to estimate what is the mass of fixed suspended solids that the phosphorus accumulating organisms will also be adding up on top of what the OHOs and on top of what the fixed suspended solids will contribute to in the system. For that purpose, we need to estimate what is the amount of fixed suspended solids that the PAOs typically have, that one as a function of the mass of PAOs, but taking into consideration what is the amount of phosphorus that they actually will store with regards to their maximum phosphorus removal accumulation. Because the more phosphorus they can accumulate, and because phosphorus is an inorganic compound, the higher the amounts of fixed suspended solids that these organisms will contribute to in the system. Let's have a look at each equation separately. First, as mentioned before, we can estimate the mass of ordinary heterotrophic organisms taking into account the flux of COD, biodegradable COD, that these organisms are going to consume on a daily basis. We need to take into account their yield. In this, approximately 0.45 kilos of these type of organisms are produced per every kilogram of COD, biodegradable COD that they consume. Of course, we need to take into account the SRT, that is the solid retention time at which the plant is being operated, and the endogenous respiration rate, or the specific mass loss rate constant of these organisms at a certain defined temperature. Typically, at 20 Celsius degrees, their mass loss rate constant has a value of around 0.24, with, the system may be operated at different temperatures, not always at 20 Celsius degrees. For that purpose, we can use this Arrhenius expression to estimate using the theta B coefficient that has a value of 0.029 to estimate what is going to be the endogenous mass loss rate constant at any temperature that the system is operated. Following the same or a similar approach, we can also estimate the mass of phosphorus accumulating organisms that will build up in the system. Important to notice that here it is essential to estimate what is the daily mass of biodegradable substrate that these organisms are going to store, because this daily mass is the one that is going to define the fraction or the yield of organisms produced in the system. Typically, they will be producing around 0.45 kilos of VSS as PAOs per kilogram of COD that they can store, similarly affected by the solid retention time and also by the specific endogenous mass loss rates constant of these microorganisms. For the PAOs compared to the OHOs, their endogenous mass loss rate at 20 Celsius degrees is lower. In this case, has a value of 0.04 with a similar theta V factor of 1.029. And these factors can be used to estimate that endogenous loss rate at any temperature that is required for the design of the system. The endogenous residue is produced from the decay of the organisms. The organisms contain certain fractions that are endogenous, particulate, and they also are unbiodegradable. And depending on the rate at which the organisms decay, they will be generated or leaving behind certain fraction of endogenous residue in the system. For the OHOs, this endogenous particulate residue is of approximately 0.2 kilos of VSS per every kilogram of microorganisms that we have in the system. For the PAOs, the endogenous residue or the mass that they will leave behind as part of that mass loss rate can also estimate it with a similar equation, but the PAOs leave behind a slightly higher fraction of endogenous particulate residue than the OHOs. PAOs leave behind around 0.25 kilos of VSS per kilogram of VSS compared to the 0.2 that the OHOs are producing. The mass of unbiodegradable particulate organics we mentioned before that is proportional to the amount that we have in the influent, so it's important to estimate what is the total or the average flow rate that the system is going to be receiving. Take into account what is the influent unbiodegradable particulate COD concentration present in the influent, and they will be proportional to the SRT, and we can estimate in this particular case the amount of solids from the COD concentration of the particulate organics using this FCV factor. That is a COD to VSS ratio with a value of 1.48 kilos of COD per kilogram of VSS. In particular, this fraction is used for all the volatile suspended solids, and it is an estimation of what could be the COD content that a kilogram of volatile suspended solids in average or typically has. So once we have estimated the 5 masses that compose of the volatile suspended solids, then we can start to estimate the masses of fixed suspended solids accumulated in the system. These fixed suspended solids that will accumulate are composed of 3 different terms. First, the fixed suspended solids present in the influent that will accumulate proportional to the influent flow rate and the SRT. Second, the contribution of the mass, active mass of ordinary heterotrophic organisms, and the contribution of the phosphorus accumulating organisms to the system. For the first term, it is important to, via a wastewater characterization, estimate what is going to be the expected influent concentration of fixed suspended solids to estimate the first term. For the ordinary heterotrophic organisms, they tend to accumulate approximately 0.15 kilograms of fixed suspended solids per kilogram of active biomass of OHOs. This fraction is mostly related to the accumulation of some minerals and metals that the microorganisms need for their metabolism. And the last and the most, potentially for the design, the most important estimation of the fixed suspended solids. That is the fraction of fixed suspended solids that the PAOs can contribute to the system. In this case, the PAOs will add up to 1.3 kilos of fixed suspended solids per every kilogram of volatile suspended solids of the active biomass of the phosphorus accumulating organisms. This contribution is directly related to the polyphosphates that the PAOs accumulate during their P removal process. It is possible to use this term directly and in a straightforward manner to estimate the contribution to the fixed suspended solids, but an additional term has been added that takes into consideration the actual amount of phosphorus that the PAOs are actually accumulating with regards to the maximum capacity that they actually can do. Why is this term added? This term is added because the PAOs, depending on how much phosphorus is present in the influent and depending on how much phosphorus the other masses contribute to the removal, they may not be completely full. When the PAOs are completely full, they can reach up to 0.3 kilograms, 38 kilograms of phosphorus per kilogram of ESS. But this is only achieved when they have reached their maximum polyphosphorus accumulation. In some cases, they have not reached it because there is not sufficient phosphorus to be removed. So that's why the term, in this case, the actual phosphorus fraction stored by these organisms is added to estimate a fraction of the actual amount of phosphorus that they have with regards to the fraction of fixed suspended solid that those polyphosphates will be adding up to the system. This phosphorus in this case, or in particular the polyphosphate, is an inorganic compound composed of 3 chains of orthophosphates, but these elements are stabilized, or they have certain ligands stabilized with magnesium, potassium, and some other minerals. And that is why when the system starts to run and they accumulate the polyphosphates, we are going to see an increase in the amount of fixed suspended solids that the total masses will have compared to another systems that do not perform the EBPR process. Now we have all the equations that can be used to estimate the total masses of solids. So now, as we can see, there are five different masses, volatile suspended solids masses, that make up the total mass of volatile suspended solids, and 3 different elements or masses that compose of the masses of fixed suspended solids. The sum of these two, the sum of the volatile suspended solids mass plus the mass of fixed suspended solids will they are composed the total mass of total suspended solids in the system. So far, we have seen the equations that are used to estimate the masses of microorganisms and other solids that will accumulate in the EBPR process. But as we could notice, it is important to estimate what is the amount of biodegradable COD that the OH chose and the amount of biodegradable COD that the PAOs will accumulate. So big part, or a big, let's say, compared to other designs, most of the efforts when doing or performing the EBPR design process, most of the efforts are focused on estimating the division of the biodegradable COD. And this division is rather important because depending on how biodegradable the chemical oxygen demand present in the infant is, also depending on the size of the anaerobic reactor, also depending on the masses of organisms that are present, the rates and the amounts of COD that this group of organisms will consume or store is going to be different. So if we have, for example, this flow scheme illustrating the most basic configuration of an EBPR process, we can see 2 stages, the anaerobic and the aerobic stage, followed by the secondary settling tank. This is the most simple configuration, it's an AO configuration. We can see that the influent is discharged into the anaerobic reactor. The sludge is alternatively recirculated through the anaerobic and aerobic stages, but also returning from the bottom of the secondary settling tank straight to the anaerobic reactor. Well, these conditions will create different effects on the way how the biodegradable COD is split. It's important to consider that the model takes into account or considers that the masses of the PAOs and the masses of the OHOs are proportionally distributed in the whole system. They are equally distributed in the anaerobic stages, in the aerobic stages, in the secondary settling tanks, and also in the waste of activated sludge and in the recirculation of the activated sludge back to the anaerobic system. Keeping this in mind, we can pay more attention to the processes that take place in the anaerobic reactor, or sometimes also called selector, in order to understand how the biodegradable COD is divided, or in this case, the consumption of the biodegradable COD is divided in these systems, so the COD is consumed either by the PAOs or by the OHOs. The COD, therefore, needs to be first defined. The total COD concentration in the inflant is composed, when we have to do an EVPR design process, is composed of 5 different concentrations. We have the soluble biodegradable organics, but in this case composed of the volatile suspended solids present in the inflant, the volatile fatty acids present in the inflant, the COD that can be fermented in the system. These are the 2 readily biodegradable organics. And afterwards, we also have the soluble unbiodegradable organics that is composed of those organics that are soluble, but that they are not degradable under biological conditions. In addition to these first 3 soluble components, we also have 2 particulate components. We have the biodegradable particulate organics, defined by XS, and the unbiodegradable particulate organics, defined by XU. These 5 different COD fractions will behave differently in or when passing through the anaerobic reactor or the anaerobic selector. First, for example, the model considers that the concentration of volatile fatty acids present in the inflant are going to be directly consumed by the mass of polyphosphate accumulating organisms. This is one of the first assumptions that the model makes. The other assumption that the model makes is that the other 3 components, the unbiodegradable soluble organics, SUI, the unbiodegradable particulate organics, XUI, because they are unbiodegradable, they will not react and they will not be converted in or when passing through the anaerobic reactor or selector. The last of these terms, that is the particulate unbiodegradable organics, the model considers that these organics are biodegradable, but because they are particulate and they have to undergo a hydrolysis and fermentation process, the model considers that relatively the anaerobic selector or reactor is not large enough to really enhance or promote a full or a significant conversion of the particulate biodegradable organics when they are passing through the anaerobic reactor. And what happens is that it considers that these 3 components are flowing through the anaerobic reactor or selector without being converted or without being affected by the biological processes that happen or take place in the anaerobic reactor. As you can see, we have already talked about 4 different elements, and we are only left with one of them, that is the fermentable COD, SF subscript I. This element, Fs subscript I, will get into the anaerobic reactor. Now this is going to be exposed or subject to the different microbial conversions, but we need to understand a little bit more about how this system works. And for that, and because now there is certain competition or certain interaction between the phosphorus accumulating organisms and the ordinary heterotrophic organisms, we need to also take into consideration what are the redox conditions that prevail in the system. One of the most important requirements to have a successful and a reliable EVPR process is that the anaerobic reactor or selector is anaerobic as much as possible, that we try to keep strict anaerobic conditions in the anaerobic reactor. That means that we need to avoid as much as possible the presence or the intrusion of oxygen or the presence or the intrusion of nitrate. However, that is not always the case. We may have nitrate or oxygen present in the inflant, depending on how the inflant is handled in the preliminary treatment units or how it is handled and transported between that unit and the primary cementation tank or any other hydraulic structure that the wastewater treatment plant may have. So we need to consider that there is the risk that nitrate and oxygen could be present in the inflant. But these are not the only 2 potential electron acceptors that may get intruded in the anaerobic reactor. We may also have nitrate and oxygen present in the sludge recycle flow, because After an anaerobic reactor, we have also, depending on the configuration, different series of tanks and reactors. We have anoxic reactors, we have aerobic reactors, followed by final settlers or secondary settling tanks, and all of them are exposed to different hydrodynamic conditions that may lead to the intrusion of oxygen, or if the denitrification step is not working at the highest efficiency possible, or naturally, if it is working but there are some traces of nitrate, we run the risk that nitrate is present in the sludge recycle and also oxygen could be present. So the model considers this potential intrusion of these two electron acceptors, nitrate and oxygen. If nitrate and oxygen present in the influent or present in the sludge are, in this case, getting intruded into the anaerobic reactor, they will not keep the strict anaerobic conditions. There will be electron acceptors that will favor that part of the fermentable COD is consumed by the ordinary heterotrophic biomass. This ordinary heterotrophic biomass is inactive under anaerobic conditions, but because these two electron acceptors are present, they may be able to start to consume part of the COD that is present in the inflow, in particular the fermentable COD. So from the initial fermentable COD that we have, we need to subtract the amounts that could be consumed because of the intrusion of nitrogen of oxygen, so that will leave us with a certain concentration of fermentable COD that could be converted, but then we get into another restriction or another limitation, and that is that this fermentable has to be actually fermented within the or in the volume of the anaerobic reactor. These anaerobic reactors depend on how much masses we have in the system that will promote the fermentation of these products. However, the anaerobic reactor selectors, compared to other systems like the aerobic systems or anoxic systems, they tend to be relatively small. So the chances that the volatile fatty acids are fermented are relatively high, depending on the amounts of biomass that we have, but we also may lose part of the fermentable COD that has been actually fermented to volatile fatty acids. So the model considers that of that fermentable COD that is available after the amounts that the OHOs could consume, the amount that is produced is or could be directly consumed by the PAOs, but also estimates what could be the amount of fermentable CODs that has been actually converted, but that because of the physical limitations or retention time in an anaerobic reactor cannot be fully consumed by the PAOs and leaks or reaches the next reactor, escapes from the anaerobic reactor and goes to the anoxic or the aerobic reactor that may be located downstream. So this is one of the most important aspects, and this is what makes this mixed culture steady-state model different from other models. That is, that it takes into account the division of biodegradable COD in the system. So how can we make the estimations of the different amounts of COD that can be fermented? Well, first, as we can see, it's important to estimate how much COD is actually or can be actually fermented in the system. For this purpose, we take into account, to estimate this amount of COD that can be actually fermented and converted, we take into account the initial concentration of fermentable COD in the influent, and we subtract the amounts of nitrate that could be contributed or contributing to this COD removal process, taking into account the amount of COD that the consumption of nitrate will lead to. And we also take into account the amount of COD, fermentable COD, that will be consumed by the OHOs, taking into account the amount of COD that is needed for the oxidation of, or in this case, for the utilization of oxygen. So this fermentable COD that is available for conversion takes into account how much we have in the influent. We need to take, as you can see in the equation, we need to take into account sludge recycle flow rates. And these coefficients, 1.86 and 3, these coefficients are based on the actual concentrations of consumption of COD depends on whether nitrate or oxygen are utilized. The 8.6 is therefore the amount of COD consumed per concentration of nitrate denitrified. It is obtained by dividing the 2.86, that are the grams of oxygen that can be replaced per gram of nitrate, divided by this factor of 1 minus FC y OHOs. This is because it depends directly on the catabolic or in the catabolism of the OHOs. And by doing this calculation, we can see that approximately 8.6 grams of COD are consumed per every kilogram or per every gram of nitrate when the OHOs are utilizing the nitrate. When they are utilizing the oxygen, then we need to take into account that approximately 3 grams of COD are used by the OHOs per every gram of oxygen consumed. And this term is also estimated based on the catabolism of the OHOs, taking into account the yields of these microorganisms. And of course, in both cases, the concentrations of oxygen in the sludge recycle and the concentration of oxygen in the influent of the wastewater treatment plant. Once we know the amount of fermentable COD that can be converted, then the model estimates what is the amount of fermentable COD that escapes from the anaerobic selector. For this purpose, we use this equation in which we have the amount of fermentable COD that can be subject to conversion divided by 1 plus S, where S is the sludge recycle ratio, divided by this term, in which we take into account this is 1 plus the fermentation, that is the first order fermentation rate constant at a temperature T. It has a value approximately 0.06 at 20 Celsius degrees. We take into consideration the anaerobic mass fraction, that is a ratio between the total volume of the reactor with regards to the sludge accumulation and the total and the concentration of solids that we have specifically in the anaerobic selector. We take into account how many compartments compose of the anaerobic reactor, anaerobic selector. This is important because most of the anaerobic selectors are not built as one single reactors. It has been seen that the more compartments we can have, typically between 3 and 5, the better the fermentation processes. So most of the anaerobic selectors are composed of at least 3 compartments, usually 4 or 5, and then we need to take into account what is the total number of anaerobic compartments that are composing of the anaerobic selector. We take into account what is the active mass of OHOs in the system, because they are the organisms as a lump sum of the total active biomass in the system. This is the mass of organisms that is going to help us in the hydrolysis and fermentation process. And of course, we take into account the influent flow rate and the sludge recycle. The term that we have in the denominator is, in this case, affected by a power number, in this case, the power n, and that is related to the compartment, is a lowercase n, and that relates to the compartment where we want to estimate the amount of fermentable COD that escapes to the system. In this example, and in most of the examples, since we want to know what is the concentration in the last compartment, lowercase n, that term is always, or tends to be always similar to the capital term n, that is the total number of anaerobic compartments. So we can use the same number of compartments for both the capital N and the lowercase n. Once we know and we have estimated what is the total amount of fermentable COD that can be converted and the amount of fermentable COD that escapes from the system, we can estimate the actual amount of COD that was, in this particular case, that is fermented and stored in the anaerobic reactor. And when we get to know this amount, then we can make the estimation that the amount or the flux of biodegradable COD that is stored by the PAOs that can be calculated based on that amount or that flux of fermentable COD that is actually converted and consumed in the anaerobic reactor, plus the flux of volatile fatty acids that the PAOs can store and that are present in the influent. As such, the total flux of biodegradable COD that can be stored by the PAOs can be a function of the flow rate times the concentration of fermentable that we have initially in the system, but that can be subject to conversion. So that means once we have subtracted the amounts that are used because of the consumption of oxygen or nitrate, minus the amount of fermentable CO that escapes from the anaerobic reactor. That is the second term in which we have to affect it by 1 plus S, that is the slurry recycle ratio. And the last term of this equation takes into account the amount of fermentable, or in this case, volatile fatty acids that are already present in the influent and that will be directly stored by the PAOs. And since we know already what is the amount of biodegradable COD that the PAOs can consume, by difference, we can estimate how much is the amount of biodegradable COD that the OHOs will consume. Because since the total biodegradable organics can be consumed either by the PAOs or by the OHOs, then if we know already what is the flux that the PAOs consume, then we can subtract that amount from the amount of biodegradable organics that we had initially in the system. So as such, the flux of COD biodegradable that the OHOs can consume will be proportional to the influent flow rate times the concentrations of the two biodegradable components, the soluble and the particulate, and subtracting the biodegradable COD stored by the PAOs. If we do this arrangement, then we have already the fluxes stored by the PAOs and the fluxes of COD consumed by the OHOs. And with these two terms, we can continue to use our mass equations to estimate the masses of OHOs, the masses of PAOs. Since these two masses are already known, we can estimate also the endogenous residues of these two groups of organisms, the mass of biodegradable particulate organics, and we will have all the elements already to calculate the total mass of volatile suspended solids that are accumulated in our system. So once the masses have been estimated based on the division of the COD, then we can start to estimate what is going to be the P removal of the system. So the most important is the amount of phosphorus that the mass of polyphosphate accumulating organisms can contribute to. This is actually the term that is going to help us in having that enhanced removal of phosphorus from the system. The amount that these PAOs can remove, or the maximum P removal by this active PAOs biomass, can be estimated based on the maximum fraction that they can store. Typically, when they have reached their maximum removal capacity, they can store up to 0.38 grams phosphorus per every gram of volatile suspended solids. The other organisms also contribute to the P removal process. Of course, in a less or a lower manner, because the other organisms do not or cannot store the same amounts of phosphorus as the PAOs. Actually, they only need a marginal concentration of phosphorus for mostly their metabolism. So these or the rest of the masses, the volatile suspended solids masses, starting with the mass of ordinary heterotrophic organisms, will store approximately 0.02 grams of phosphorus per every gram of volatile suspended solids. In all these terms, you can see that the amount of phosphorus consumed by each group of organisms is proportional to the fraction that they can store by the mass of the organisms present in the system. We can also see it for the PAOs, divided by the influent flow rate and the solid retention time. So the only term that is actually changing is the amount or the fraction of phosphorus that each organism or that each mass can store. Therefore, in a similar manner, the mass of endogenous residue of the PAOs, the mass of endogenous residue of the OHOs, and also the mass of particulate on biodegradable organics, they will contribute to only certain fraction, or in this case 0.03 grams per every gram of VSS that these masses contribute to in the system. As such, if we want to know what is the total amount of phosphorus that the system potentially can remove, then it will be just a matter of summing up the amount that the PAOs remove plus the amount of the OHOs, the endogenous residues, and the accumulation of particulate unbiodegradable organics. However, we call it system potential because even if the PAOs can store up to 0.38 grams of phosphorus per gram of VSS, they may not be able to reach their full capacity. And that is because they are limited by the amount of phosphorus that we have present in the influent. And of course, and logically, if we want to meet specific discharge standards, the concentration, or in this case, the potential removal of phosphorus of the system has to be higher than the amount of phosphorus that we have present in the influent. Sometimes that is not the case, and we may have certain amounts of phosphorus that are left and that cannot be removed in an activated sludge system. So if we take that into consideration, the actual amount of phosphorus that the system can remove will be the minimum concentration between what the system can potentially remove and what we have present in the influent. And this will be the actual removal of phosphorus by the EBPR process. However, we need to take into consideration for different further calculations what is the actual amount of phosphorus that the PAO can remove. For example, if the PAO can remove up to 0.38 grams of phosphorus per gram of BSS, when maybe the concentration of phosphorus in the influent are as high or higher than, let's say, 20 or 30 milligrams per liter for a hypothetical case, then possibly they will reach the maximum capacity. But that is not always the case. We have to take into account only what is present in the influent and therefore estimate to which extent the PAOs are, in this case, filled or completely full by the presence of phosphorus. For that purpose, we need to calculate the fraction of phosphorus that is actually present in the PAOs. For this purpose, we take into account what is the maximum mass of phosphorus that the system has actually accumulated. We do it by adding this term, which we take into account the influent flow rate, the SRT, and the concentration of phosphorus that the system has actually removed. And in order to know only what the PAOs are contributing to, we subtract the amount of phosphorus that is present in all the volatile suspended solids masses, but excluding the mass of PAOs. In this term, the difference between the mass of volatile suspended solids when we exclude the mass of PAOs will leave us or give us only the sum of the mass of OHOs, the mass of the endogenous residues, and the mass of the particulate biodegradable organics. So this term in the upper part will help us to know the amount of phosphorus that, in this case, the mass of phosphorus that is actually stored in the PAOs. And dividing this term by the mass of PAOs that we have actually in the system will help us in estimating what is the actual amount of phosphorus that the PAOs have stored in their cells. This term is important because previously we have calculated the masses of volatile suspended solids, these first 5 masses. But when we start to, or we want to estimate the mass of fixed suspended solids, we can see that in the last term, we need to use that fraction of phosphorus that the PAOs have actually accumulated, because that will affect the amount of fixed suspended solids or inorganic suspended solids that will be built up in our activated sludge plant. So by estimating that fraction, we now have all the required elements to estimate not only the VSS, but also the FSS or inorganic suspended solids in our plant. And we are now in the position of being able to estimate the total mass of solids that the EBPR system will accumulate. But before that, it is also important to estimate what is the actual amount of phosphorus that is present in the total suspended solids. So not only in the PAOs, but also in the total suspended solids. And the main reason is that when we are doing or when we are handling the solids, not only the sludge or the waste of activated sludge that is extracted from the activated sludge plant, but also, for example, when we take into account the loss of solids through the effluent of the activated sludge system through the secondary clarifier, those solids contain phosphorus. And that phosphorus will be also increasing in terms of total phosphorus, will be increasing the amount of phosphorus that our plant is actually discharging into certain receiving water body on a certain point. As such, it becomes important to estimate what is the amount of phosphorus present in the total suspended solids of the plant. And we can do that by taking into account the fraction of phosphorus that the different masses of volatile suspended solids can store, divided by the mass of total suspended solids. But it's important to notice that here we are not including the mass of PAOs, because the mass of PAOs has a different fraction of phosphorus accumulated, and that is the actual fraction of phosphorus that we have calculated previously. Both terms divided by the mass of total suspended solids, and this will help us in estimating what is the fraction of phosphorus in the VSS. We still need to add what is the amount of phosphorus that is present in the fixed suspended solids. And that when we do it by considering that fraction that the fixed suspended solids can contribute to, and all the terms divided by the total mass of suspended solids. As such, now we have all the elements to estimate what is going to be the expected phosphorus concentration, total phosphorus concentration in the effluent of the activated sludge plant that is performing the AVPR process. For that purpose, we need to calculate what is first, using the previous equations, the actual contribution or peer removal of the system. We subtract that from the influent. If this is, or the concentrations are more or less similar, it's going to lead to a very low or almost negligible concentration. But since we are also dealing with the total phosphorus concentration, or we want to take into account the total phosphorus concentration, we need to add the phosphorus that is present in the solids that are lost through the effluent. Most of the secondary settling tanks do or work at a very high efficiency. They are able to handle concentrations of between 2,500 up to 6,000 milligrams of TSS per liter, and they only leave a little bit, like 10, 30 milligrams per liter, typically in the effluent of the plant. So the efficiency of the secondary settling tanks is very high. However, and nevertheless, the carryover of solids through the effluent will also, because it's composed of biomass, because it's composed of solids, because it's composed of PAOs, will also contain phosphorus. And if the regulations aim to limit the discharge to the concentration or total concentration of phosphorus, then it's important to also take into consideration how much of phosphorus is present in the total suspended solids. For that purpose is why we need to consider this fraction of phosphorus, and that can be computed based on the concentration of total suspended solids expected to be in the effluent, as mentioned before, typically between 10 and 30 milligrams of TSS per liter if the system is working efficiently, and multiplied by the fraction of phosphorus expected to be present in the total suspended solids. This will give us the total phosphorus concentration in the effluent, and then we are now in the position of calculating what could be the expected total phosphorus concentration in the effluent of the wastewater treatment plant. Since now we have all the elements, we can calculate also the total mass of volatile suspended solids, the total mass of fixed suspended solids, and the total mass of solids that will be accumulated in our EVPR system. And there are a few ratios that can also be used to assess the efficiency and to assess how the system is performing. Some of them are, for example, the fraction of volatile to total suspended solids, or the fraction of active biomass to volatile suspended solids. The first one will give us certain degree, or will help us to estimate to a certain degree the accumulation of organics. So what is the fraction of the total suspended solids that are still composed of certain organics? Typically, for EVPR systems, this value tends to be relatively lower than systems that perform only the organic matter removal process. For example, an organic matter removal process will typically have values or fractions higher than 0.85, whereas EVPR process can have concentrations as low as 0.65 to 0.75, depending, of course, on the amount of phosphorus that the systems accumulate, because the phosphorus adds up or contributes to the accumulation of fixed suspended solids. The other term that is typically used is the FAV fraction. The FAV fraction relates to the amount of active biomass that we have with regard to the total mass of volatile suspended solids. In this case, it can give us certain information related to how stable the sludge is. In this case, the active biomasses, excluding nitrifiers, if nitrification takes place, we need to add it, but excluding nitrifiers, the active biomass is composed of the mass of ordinary heterotrophic organisms plus the mass of phosphorus accumulating organisms divided by the total concentration or total mass of volatile suspended solids that we have in the system. The lower the value, the more stable the sludge is considered to be. Values lower than 0.2 indicate that the sludge contains less than 1/5 of the total volatile suspended solids composed by living active organisms, so it's considered to be already stable, whereas values higher than 0.2 will will tell us that the fraction of active biomass is higher than 1/5 in the system, and depending on the SRT, longer SRTs will tend to lead to higher FAV factors, sometimes as high as 0.5. That will tell us that most of the sludge is composed of living active biomass. If we have that sludge more active, then it's important to do and handle the sludge properly in order to stabilize it as it is recommendable depending on the local conditions. If the sludge is lower than 0.2, and that happens when, for example, the SRT is relatively long, then that sludge should be considered already stable and could be handled in a different manner compared to the other types of sludge that have a higher FAV fraction. We have estimated already the masses, and now we can also start to calculate what should be the volume of our EVPR system. The volume of our EVPR system can be estimated based on the total mass of solids that we have previously computed, but now we need to select an average TSS concentration for the aerobic reactor. Typically, or in average, the ranges can go from 2 to 6 kilograms of TSS per cubic meter, and typically values of around 3 to 4 are used when the systems are sized. Once we know the volume of the system, we can also estimate what is going to be or what should be the volume of our anaerobic reactor or anaerobic selector. For that one, we need to revise the fraction of the anaerobic selector. Strictly speaking, the fraction of the anaerobic selector relates to the anaerobic mass fraction that is present in the system divided by the total mass of solids that we have in our complete EVPR system. That means that we need to take into account the volume, or that this fraction relates to the volume of the anaerobic reactor times the concentration of solids that we expect to have in the anaerobic reactor, divided by the total mass of solids of the system. That is the volume of the reactor times the expected or typical concentration of TSS that we expect to have, or that we have selected for the design of the activated sludge system. For most of the systems, or for most of the configurations, for example, for the A2O, the EO, or the Bardeenford configurations, for these systems that do not have different internal recycles compared to, for example, the UCT or the modified UCT configuration, for all of them, the concentrations of solids in the anaerobic reactors will be very similar to the concentration of solids in the aerobic reactors. What means that if the concentrations are more or less the same, this term could be disregarded in the equation, and then the anaerobic mass fraction can be estimated only as the ratio between the volume of the anaerobic reactor divided by the total volume of the system. What means that since we don't know yet what is going to be the volume of the anaerobic reactor, that volume can be estimated based on the anaerobic mass fraction times the total volume of the system that we have previously calculated. And this anaerobic selector needs to be divided in different compartments, depending on the number of compartments that we have considered previously when we did the division of the COD for the anaerobic selector, typically between 3 and 5 compartments with identical volume. The waste of activated sludge is a very important parameter because the waste of activated sludge will help us in controlling the solid retention time. And the solid retention time is the most important design and operating parameter for an activated sludge system, and is not different from an EBPR system. For the removal of the excess of sludge or the waste of activated sludge, we have two alternatives. One of them is to remove the excess of sludge from the bottom of the secondary settling tank. And for this particular condition, we need to know first the concentration of solids in that waste of sludge, and we already know the volume of the reactor and the total mass of solids that we have in the system. As such, the waste of activated sludge can be computed as or in terms of the volume of the reactor times the concentration of TSS, that is basically the total mass of solids accumulated in the system, divided by the SRT that we have used for the design of the system, times the concentration of TSS in the waste of activated sludge. This is one of the most typical and common ways to control the waste of activated sludge in an activated sludge plant. However, there are also some other practices that have been promoted lately. One of them is not to do the waste of sludge from the bottom of the secondary settling tank, but to do it directly from the last reactor, from the aerobic reactor, or from a line that connects the aerobic reactor with the secondary settling tank. If we do that practice and the waste of activated sludge is wasted from the end of the aerobic reactor or from a line that connects the aerobic and the secondary settling tank, then the calculations can be a bit different. Because by wasting from this point, the concentration of total suspended solids in the sludge waste is going to be very similar or identical to the concentration of solids that we have in the aerobic system. What means that the concentrations, if they are the same, then we can disregard the concentrations in the calculation. What means that the control of the waste of activated sludge will be only a portion or a fraction of the volume of the reactor divided or affected by the solid retention time at which we are operating the system. And this makes the control of the SRT much more reliable because we don't have to measure the concentrations in the system for a day-and-day operation, and neither we have to estimate the concentration of solids in the waste of activated sludge. What happens if we use or we practice the waste of activated sludge from the bottom of the secondary settling tank? Of course, there are pros and cons of both systems, but the fact that this waste or this practice can be a bit more reliable, since we only depend on the SRT or in a fraction of the volume of the reactor, can have strong benefits to keep a well and a stable SRT for the system, and is not or cannot be easily objected, since the SRT is the most important design operating parameter of an activated sludge system. Once we have estimated the waste of activated sludge and that we have also performed and calculated different control parameters like the waste the masses, volumes, etc. Now we can start to discuss the requirements, what our system needs to be able to perform properly. The first one, and also being heterotrophic organisms, the ones that govern or drive most of the biological processes in this eVPR system, then all of them have oxygen requirements. So we need to calculate what is the oxygen demand. The oxygen demand first can be estimated based on the flux of oxygen that the PEOs need. This flux of oxygen, or the oxygen demand that they have, is composed of the oxygen they need for synthesis, the oxygen that they need for endogenous respiration, and for synthesis this is directly proportional because it's part of the catabolism, or the catabolic pathway, is directly proportional to the amount of COD that they store in their cells. The second term, that is endogenous, this depends on the decay rate of the organisms. So for that one, we need to take into account what is the amount of biodegradable COD that disappears from the system, subtracting the amount that remains based on the fraction of endogenous residue they leave behind after the loss, or the loss of masses, or of the biomass of the PEOs, affected by the FCV factor, the endogenous respiration rate, and the active biomass concentration in the system. These terms can help us in the estimation of the oxygen demand that the PEOs will have. The whole equation can also be worked out, since we already know that the masses of PEOs is a function of the flux of soluble biodegradable organics that they can store, and of course based on the stoichiometric parameters of this group of microorganisms. And this term will help us in the estimation of the oxygen demand by the PEOs. For the OHOs, we can do a similar analysis, a similar estimation, but in this case, the amount of oxygen needed for the synthesis of new cells will be proportional to the biodegradable COD that these organisms consume, based on the division of COD that we have previously made, plus the amount of oxygen required for the endogenous respiration. And this is also proportional to the amount that they leave behind after they are exposed to the endogenous respiration processes. Once we know this flux, or the oxygen demand by the OHOs and the oxygen demand by the PEOs, then we can be able to estimate what is the total oxygen demand of the system, or what is also called the daily carbonaceous oxygen demand of the eVPR process, composed of the oxygen demands of these two groups of organisms. Another important parameter is related to the nitrogen requirements. We have to take into consideration that these organisms are volatile, are organic compounds, are living organisms that also need nitrogen for the synthesis of new cells, as part of, for example, the different types of tissues that they have to build up. And for that, they will also contribute to the removal of certain amount of nitrogen. That amount of nitrogen they need for the synthesis of new cells can be estimated based or using this equation, where the amount that they require is function of the nitrogen content of the volatile suspended solids, or pretty much related to the amount of nitrogen they need for the synthesis of new microorganisms. This fraction multiplied by the total mass of volatile suspended solids and divided by the influence flow rate and the SRT will help us in calculating the concentration of nitrogen that the eVPR system will contribute to. This, if the system is designed for nitrification and denitrification, that means when we are also interested in implementing a nitrogen removal process, this implies that this NS concentration needs to be taken into account when designing the nitrification and the denitrification processes. Last but not least, we have the COD mass balance. The COD mass balance is one of the most useful tools that we can have to check and confirm that all the calculations are correct. For that purpose, then we need to do first an estimation of what is the total COD that the system receives, and what is the amount of COD that leave or that exit the system. the total amount of COD that our system receives is the total influent COD flux. Whereas the amount of COD leaving, well, this is not completely correct, but the amount of COD that leaves the system does it via the liquid, for example, via the effluent or the waste of activated sludge, the liquid part, via the solids, because we are subtracting part of the solids from the system, and it's not completely correct because it is via the gases. In the end, there are, or we cannot consider certain COD gases leaving the system, but we do take into account what is the amount of oxygen that the system needs for the oxidation of the organics. And this is more or less the gas phase that contributes more or less in certain manner to the removal of COD or the oxidation of COD from the system. And that is directly proportional to the oxygen consumption. As such, the COD input can be estimated based on the influent flow rate and the total COD concentration. Whereas the COD outputs are, for example, the ones present in the waste of active sludge. So in this case will be the waste times the concentration of soluble unbiodegradable organics, the concentration of soluble unbiodegradable organics in the effluent of the plant, plus the amount of COD present in the waste of activated sludge, taking into account the FCB factor, the flow of the waste of sludge, and the concentration of volatile suspended solids in that waste of sludge, plus the amount of oxygen that the system needs for the carbonaceous oxygen demand. This can be worked out further since we know that the influent is equal to the flow rate in the effluent plus the flow rate in the waste of active sludge. Also, because we know that the waste of activated sludge is proportional to the volume of the reactor divided by the SRT, and because we also know that the concentration of volatile suspended solids in the system, if we waste from the aerobic reactor or from a line that connects the aerobic reactor with the second descending tank, the concentration of volatile suspended solids is going to be similar to the concentration that we have in the aerobic reactor. As such, the COD outputs could be, the calculations can be simplified because we can have the influent flow rate times the concentration of unbiodegradable soluble organics in the influent, plus FCB times the total mass of solids that we have in the plant divided by the SRT, and plus the oxygen demand that is needed for the oxidation of organics. For the mass balance, the COD input has to be equal to the COD outputs, so we can come up with this final comparison between the total COD and the outputs of COD, and if all the calculations are correct, there shouldn't be a difference, or these two values, the values on the left and on the right, they should be almost identical. There is certain margin of error allowed because of the rounding of certain numbers or because certain simplifications, but still the tolerance must be lower than 0.1% to confirm that all the calculations are correct. If it is more than 0.1% or even higher, then it's important to revise carefully the different calculations and try to find out where certain omission or a certain typo may be present. And that's why the COD mass balance is one of the most important tools, because it can help us to self-confirm that all the calculations are correct.